Okay, so we're going to talk about acid strength and what makes a strong acid and a weak acid and a strong base and a weak base. The definition is pretty much based on whether or not something ionizes in solution. So if you have something that's a strong acid, it's considered a strong electrolyte. In other words, it will 100% ionize. So we see that a strong acid is 100% ionization, and so is a strong base. So anything that's considered a strong acid or base will 100% ionize, meaning that when you have this reaction, let's say HCl, it's going to completely dissociate to give you H plus and Cl minus, or in other words, it's going to react to create hydronium and chloride. If you don't have 100% ionization, you have a weak substance. So a weak electrolyte, a weak acid, and a weak base is something that does not ionize 100%. So that would be anything that is less than 100% ionization. And if you don't have 100% ionization, we can't really draw it as a single arrow reaction. So we have to draw it as a double arrow equilibrium type of reaction. Okay, so if we think about an example of a strong acid and a weak acid, a strong acid would be something like hydrochloric acid, as we mentioned on the previous slide. And HCl, when you put it in water, it's going to fully dissociate. So HCl is going to break up, and the only thing we're going to have in there are hydronium ions and chloride ions. And because it's 100% ionization, it's really easy to figure out the concentration of H plus in solution, right? So essentially, if I have a 1.0 molar solution of HCl, right, that means that the concentration of H plus is also 1 molar. Okay, so um, I could say, well, let's get rid of this guy here. 1 molar HCl. I know that this reaction 100% ionizes, so I'm gonna draw it like this, even though I know it really gives me a hydronium. It's a single arrow because we get a full reaction in the forward direction, even though everything's in equilibrium. This goes so much far to the right. The equilibrium constant is so large that we can draw it as a single arrow here. And we just have these ions floating around in solution. So if I have 1.0 molar HCl in that solution, right? In other words, let's say if we have a liter of water, right? That means I have 1 mole of HCl I put in there. So it gives me a 1 molar solution. Well, then I'm also going to make 1 mole of H plus and 1 mole of Cl minus, which means I'll be 1.0 molar H plus and 1.0 molar Cl minus in that solution. All right, now let's go back to our slide here and look at an example of a weak acid, something like HF. If you look at this solution, you see what's happening, in the before and after here. Once I put HF in there, not only do I have F minus, and I also have H3O plus, but there are some molecules that don't totally ionize, and I still get HF molecules in solution. So before for HCl, right, I only had chloride anions and hydronium cations. Now I've got three things in solution. I've got cations, anions, and the original molecule, which doesn't dissociate. So because it doesn't dissociate, it's a weak substance. And that's really the way we can determine whether or not something is a strong acid or a weak acid. It has to do with the degree of dissociation. And so for HF, if I put this in water, what's going to happen is a little bit of it's going to react in the forward direction, and it's going to lose some proton, but at the same time, this can react in the reverse direction to form HF, so I have all three things in solution. Now, if I consider having a 1 liter solution of water, right, and I've got 1.0 moles of HF in there, right, that means that I have a 1 molar solution of HF. But how much H plus and how much F minus do I have? Well, uh, this is an equilibrium reaction, so I have to treat it like an equilibrium. How would you figure out X and X for an equilibrium if we know we started with 1.0 molar? Well, we would have to work in the ice box, right? So whenever you're dealing with a weak acid, you got to use the ice box to figure out what that concentration of H plus is. All right. Um, Here are some examples of strong acids. I will expect you to know every single strong acid listed up there, right? If I write HCl, HBr, HI, you need to know that's a strong acid. It's 100% ionization. You also need to know that nitric acid, perchloric acid, and sulfuric acid, these are all strong acids. Okay, now the weak acids that I really want you to be able to know are hydrofluoric, acetic, carbonic, right? Those are the ones I really expect you to be able to know. Formic and phosphoric, you don't really have to know. These are all oxyacids. So the only oxyacids that are strong in comparison here are nitrics and sulfuric are the only two, and of course perchloric. These are the only three strong acids. Now sulfuric acid's interesting because um, the first proton that comes off, that's a strong event, but the second proton is not as strong. And we'll talk about that when we talk about diprotic acids. So I do expect you to know your strong acids and your weak acids. Um, Now, for bases, a strong base will also completely dissociate. So if you think about a base like sodium hydroxide, you could say, oh, well, you know, when I have NaOH in solution, it's going to dissociate to create sodium ions and hydroxide ions, right? So that's a Arrhenius definition there. As a base is anything that dissociates to create OH minus in solution. And so for strong bases that are hydroxides, the concentration of hydroxide in solution is going to be equal to the concentration of the strong base in solution times the number of hydroxides, and that gives you the concentration of hydroxide. So in this example here, what we're looking at for sodium hydroxide is we have just one hydroxide in the formula. Okay, so for instance, if we had a 1.0 molar sodium hydroxide solution, the concentration of OH minus then is equal to 1.0 molar multiplied by 1, which is just 1 molar. Now, let's say we're dealing with a different type of strong base that's got two hydroxides on it. For instance, we want to look at, let's just say calcium hydroxide. What happens with calcium hydroxide, let's say we had a 1.0 molar solution of CaOH2, right? And we want to know what the concentration of OH minus is. Well, the concentration of OH minus in this instance is equal to 1.0 molar, which is the concentration of our strong base, multiplied by the number of hydroxides. In this instance, there are two hydroxides there. So we multiply that value by 2, and this gives us 2.0 molar, right? And this makes sense because if you think about calcium hydroxide, right, if we were to put this thing in solution and it were to act as a strong base, it would completely dissociate and we would be left with Ca2 plus and 2 hydroxides, right? So the hydroxide concentration is 2 of the calcium hydroxide concentration. Okay, so most strong bases that we run into are hydroxides. We also have some weak bases though, and things like ammonia, for instance, is a classic example of a weak base. And when we look at ammonia, we talked about this reaction before. It doesn't fully react to form hydroxide in solution. So when NH3 reacts with water, we can form ammonia, but we don't write this as a single arrow reaction. we write as a double arrow reaction, and that means we'll have all three components present in our solution: NH3, NH4 plus, and hydroxide. So if you look in our solution, you'll be able to see all of those things: OH minus, NH3, and NH4 plus. Just like with an acid, when you have a dynamic equilibrium for a weak acid, you also have the same thing for a weak base. And if you have an equilibrium, you have to use the ice box to figure out your concentration of OH minus. Okay, so much less than 1% ionization in water, right? That's one thing I want to point out here, is these weak acids and weak bases, they don't ionize much. Strong acid is 100% ionization. For a weak acid, it's really never gets above 5%, and for a weak base, you're usually much less than 1% in terms of the ionization. So you don't create a lot of H plus or OH minus in solution. All right, so what's really happening, we say H plus interchangeably with hydronium, but all aqueous solutions then contain hydronium and hydroxide ions. Now, if you have an equal balance of hydronium and hydroxide, you have a neutral solution, okay? And so when the concentration of H plus equals the concentration of OH minus, that gives you a value of 1.00 times 10 to the minus 7th molar. Now the question is, how do we come up with this concentration? Well, if you just have a regular solution of water, it actually will auto-ionize. It doesn't happen often, but every once in a while it will auto-ionize. And we talked earlier about how you can have what are known as amphoteric substances, right? So if you remember from Unit 1 lecture, an amphoteric substance is something that can act as an acid or a base. And we saw instances where water reacted with HCl to act as a base, and where it can react with ammonia to act as an acid. So with the autoionization of water, if we have a sample of water, every once in a while, it doesn't happen often, but every once in a while, two water molecules can react with each other, and you can get an autoionization process where one water molecule will accept a proton, acting as the base, and the other water molecule will donate the proton. So this water molecule over here, this is acting as our base. It's accepting that proton. It's coming to pick it up. So if you want to think of it as the Lewis base, it is the electron donor. And so if I look at that as the electron donation, I could say, well, that means that here we'll use a different color. The proton is going from here over to here, right? And that means that this is our Lewis acid, because it's giving that proton up. It's also accepting the electrons. And when that, so the arrows I'm drawing are for the electrons. When that occurs, your Lewis acid is going to be left as a hydroxide. Your Lewis base is going to be H3O plus, and we'll have this. Okay. So if we measure the concentration of H3O plus and concentration of hydroxide in solution, we can get an idea of the equilibrium constant. So if we were to write an equilibrium constant, K, for this, it would be products over reactants. But if you look in the reactant side, both of those reactants are a liquid. So that means that their concentration isn't changing over time. And so the equilibrium constant for this is just H3O plus multiplied by OH minus. Okay, and this is known as the Kw value, right? The equilibrium for the autoionization of water, we use Kw, and it always has a value of 1.00 times 10 to the minus 14th. Okay, so what does that tell you? Well, this equilibrium that exists, right? This is really an equilibrium, and it really lies heavily to the left, right? You don't make a lot of products. So this autoionization, doesn't occur very often. It's very, very, very rare that it occurs, but it can occur every once in a while. And we measure it at room temperature. It's 1.00 times 10 to the minus 14th. So we could say, all right, well, that means that if that were the case, right, what is the concentration of each? Well, in a neutral solution, the concentration of H3O plus would equal the concentration of OH minus, and if we don't know what that is, this is X, and this is X, right? That would give us 2X, and that equals 1.00 times 10 to the minus 14th, right? So we could calculate this by just taking, run out of room here, we could calculate this by just taking 1.00 times 10 to the minus 14th and dividing it by 2, okay? So we see that X equals 1.00 times 10 to the minus 7th, right? And that's how we come up with this value that you see on the slide here, 1.00 times 10 to the minus 7th, is from the autoionization of water, the equilibrium constant that results from that. And if you have equal amounts of H plus and OH minus, that means that your concentrations are equal and your solution is by definition a neutral solution. Now, if those concentrations aren't in equal amount, then you no longer have a neutral solution. And we see that when the concentration of H plus is greater than the concentration of hydroxide, that gives you an acidic solution, and vice versa for a basic solution. So here, what we see is that our concentration of hydronium is actually greater than the concentration of hydroxide. We're out of balance. And that gives us an acidic solution. Now, for a basic solution, the concentration of hydroxide is actually greater, and that's what creates our basic solution. So that's how we define an acidic solution versus a basic solution versus a neutral solution. It's all dependent on the amounts of hydronium and hydroxide you have present in that solution. Now, one way we express concentrations of hydronium hydroxide is by pH. And pH is a negative log scale. And if you think about it, those values we're dealing with are really, really small values. And it's hard to think about concentration on the order of 10 to the minus 7th. So in order to make it a more manageable number, we take a log of it, and we take the negative log of the concentration. So in order to find the pH of a solution, you have to know the concentration of H+. Now let's think about neutral solution. We know that the concentration of H+ in neutral solution is equal to 1.00 times 10 to the minus 7th molar. That's a really small number. So my pH then is just equal to the negative log of that value. And when I take the negative log of 1.07, this gives me a value of 7. And that's why we say neutral solutions have a pH equal to 7 at 25 degrees C. Okay. Now, this is a logarithmic relationship. So it's a log base 10 unit, which means that if you have the pH, you could also find the concentration of OH minus, right? So it reasons that the concentration of H plus is going to be equal to 10 to the negative pH. So for a neutral pH, pH is 7, concentration of hydronium ion is 10 to the minus 7th, right? 1.0 times 10 to the minus 7th. So you can go both ways with that. pH is a unitless, even though concentration of H plus must be in molarity. This is a similar effect to what we saw with the equilibrium constant. We're not taking the concentration of H plus, we're taking the activity of H plus, and we're just assuming that the activity coefficient is equal to 1, so the molarity equals the activity. So in reality, pH is a unitless value. Now, this is a negative log relationship, which means that as concentration of H plus increases, the number you get is going to be smaller. So at really acidic solutions that have high concentrations of pH or high concentration of H plus are going to have very low pH values. Really basic solutions that don't have a lot of H plus, they have a low concentration of H plus, are going to have high pH values. And then, of course, we have pH 7, that is equal to neutral. So the lower the pH, the more acidic the solution, and the higher the concentration of H+. The higher the pH, the more basic the solution, the lower the concentration of H+. And if you think about this, 1 pH unit difference corresponds to a factor of 10 difference in acidity because it's a log 10 unit. So what's the difference between a pH 2 solution and a pH 3 solution? Well, the solution at a pH of 2 is actually 10 times more acidic. It's got 10 times the amount of hydronium ion in it than the pH 3 solution. And our typical scale for pH is 0 to 14, where pH of 0 gives us a hydrogen ion concentration of 1 molar. So anything that's really, really acidic has a pH close to 0. Our strong acids are close to 0. There are some super acids that you can have pH values that are in the negative. And then anything that's really, really basic, like a strong base, gives us a value of 14. So when your concentration of hydroxide equals 1 molar, you can have a pH value of 14. All right, so here's what our pH scale looks like, and here's how it corresponds to concentration of H+. So you see over here, when you have really low values, it corresponds to really large numbers of H+. But when you have really high values, more basic, you have really, really small numbers of H+, right? 10 to the minus 14th concentration. So it's an inverse relationship. As concentration of H+ increases, right, that's going to give you a corresponding drop in the pH. Now we can also calculate pOH by taking the negative log of the concentration of H+ or OH minus. So, you know, just from this this idea that you can have pH and pOH, you might understand what the letter P means. P just means negative log of whatever comes after it, right? So if I have pOH, that means negative log of OH minus concentration. If I have pH, that means negative log of H plus concentration. All right, so in order to find the concentration of OH, or the pOH of a solution, we need to know the concentration of OH minus. And so we could say, okay, well, the concentration of pOH in water for autoionization, if we have a neutral solution, our neutral solution is going to have equal amounts of hydroxide and H+. So what I could say is, well, you know, I know concentration of H+ times the concentration of OH minus has to equal 1.0 times 10 to the minus 14th. Okay. Well, what is that? Well, the concentration of H+ and concentration of OH minus then have to equal 1.0 times 10 to the minus 7th, right? Because 1.0 times 10 to the minus 7th multiplied by 1.0 times 10 to the minus 7th equals 1.0 times 10 to the minus 14th. Okay. Let's say I thought about pOH and pH here, right? I'm just going to take the negative log of this entire expression. 1.0 times 10 to the minus 7th times 1.0 times 10 to the minus 7th. And this equals 1.0 times 10 to the minus 14th. Okay. So what does this do then, right? I've got negative log of that, negative log of that, and negative log of that. Negative log of 1.0 times 10 to the minus 7th is 7. Negative log of 1.0 times 10 to the minus 7th, 7. Negative log of 1.0 times 10 to the minus 14th is 14. So what I've just derived here is I've shown that the pH plus the pOH is equal to pKW, or pH plus pOH equals 14. So if I know pH or if I know pOH, I can always find the other one, right? So let's go back to our solution that we're dealing with here. let's say we have a basic solution. Well, in a basic solution, we have a really high pH, something that's greater than 7. So let's say you have a pH equal to 10. What's the pOH? Well, we know that pH plus pOH is equal to 14. So 14 minus pH should give me the pOH. 14 minus 10 equals 4. So my pOH then is equal to 4. What does that tell me? Well, that just tells me that whenever I have a really basic solution, the pOH will be small and the pH will be high. And this makes sense because it's a negative log relationship. Anything that's acidic is going to have a really large pOH and a really small pH. And then, of course, anything at neutral is pH 7. And so if you look at how pH and pOH correspond, they're complements of one another, right? So at neutral pH, they're both, or neutral solutions, they're both at 7. Anything acidic, the pH will be lower, the pOH will be higher. Anything that's basic, the pOH will be lower and the pH will be higher. Okay, so like I said, you can use pOH and to find the pH of a solution and vice versa. And this is from the fact that, you know, the concentration of H3O plus and OH minus is equal to 1.0 times 10 to the minus 14th, which is the Kw value. So in theory, if you know the concentration of one, you should be able to calculate the concentration of the other pretty easily by just taking the Kw and dividing it by the concentration you know. And also you can look at pH and pOH, right? If we distribute a negative log into that, that would give us the negative log of H plus the negative log of OH minus, which equals the negative log of Kw, which is 14. And that's where we get to pH plus pOH equals 14. So this is one way we can determine the strength of an acid. We can look at the pH of the solution it creates. For instance, if we have hydrochloric acid, which we know is strong, it's going to 100% ionize, and it's going the concentration of HCl we have is going to completely dissociate into H+. So if you have a 1 molar solution of HCl, right, all of that dissociates to create a 1 molar concentration of hydronium ion, H3O+, and the pH of that would be, you know, the negative log of 1, which is 0. So that's a really strong acid, obviously. If you have pHs that are a little bit higher, they're weaker acids. The same could be said about a base. If we have something like sodium hydroxide that's 1 molar concentration, we know it 100% ionizes, and so it's going to create 1 molar hydroxide ions. Well, you know, the pH of that would be 14 then, because we know the pOH of 1, the negative log of 1 is 0. So if we have a pOH of 0, that means the pH has to be 14. So a strong base is synonymous with a really high pH value, and the the weaker bases have pH values that are above 7 but not quite as high as 14. Another way we can look at acid strength is by looking at the equilibrium constant. So if we think about our acids and bases, and each instance here, if we have an acid, it's going to dissociate to create its conjugate base A minus, and also hydronium ion H3O+. The degree of ionization depends on how much these equilibria shift towards the right. So if you have a strong acid, it's going to go way, way farther over to the right, where if you have a weak acid, your equilibrium constant K won't be as large. Same thing could be said about the base. A really strong base, large equilibrium constant, it's almost a straightforward reaction, 100% ionization. A weaker base, the equilibrium constant K is going to be much lower. So we can look at the position of the equilibrium to indicate the strength of the acid or the base. And this position of the equilibrium, it depends on the attraction of the cation and the anion, really. So if we think about this acid, let's think of HCl, for instance. And we have HCl in solution, and it reacts with H2O. Okay. We say, all right, well, we get this equilibrium in theory, where we create hydronium ion H3O plus AQ. and Cl minus. So this is kind of what really happens in solution. We could also write this as a dissociation where, HCl goes to H plus and Cl minus. So you'll also see it written like that, of course. But we'll work with the bottom reaction. Now, the degree of dissociation is kind of dependent on the strength of the interaction between the anion and the hydronium ion. So, how readily does that conjugate base here, this is our conjugate base of our acid, how readily does that react with the hydronium ion? Right, that's the question. And so for a strong acid like HCl, we see that there is really no reaction in the reverse because there's no attraction between these two ions. So this is written as a single arrow forward reaction because there is no attraction between the ions. Now, if you have a weaker acid like hydrofluoric acid, when we put it in water and we create this equilibrium, we get hydronium ion H3O plus and F minus. Well, it turns out that F minus here does want to interact with H3O plus. So that interaction, there's a stronger attraction between the ions, and what we'd say then is that the F minus, which is the conjugate base of our acid here, this is a much stronger base than Cl minus is because it will want to interact and we'll get a back reaction, and that's why we have this equilibrium that's created. And because it's going to interact with hydronium ion and react in the reverse direction, well, now we're losing product, so that's going to decrease the equilibrium constant K for this reaction. So if you think about writing an equilibrium constant for any kind of acid dissociation, no matter if you look at it from an interaction with water or just a dissociation, you're always going to get the same thing, right? If we're looking at the first step here, Ka is going to equal products H3O plus and A minus, right, over reactants HA. We're not going to include water because it's a liquid, and the same can be said here for reaction 2, which is the shorthand version where our products are H plus and A minus, right, and our reactant is HA. So these two are equal to one another. This is a special type of equilibrium for an acid dissociation, so we call it an acid dissociation constant. Whoops. And we give it a value of Ka. So this is known as the acid dissociation constant Ka. It's always given from the dissociation of a proton from an acid, right? That's the reaction we always write for an acid dissociation constant. So here are some Ka values for strong acids, just to give you an idea. Hydrobromic acid, really a strong acid, 1 times 10 to the 9th. So it's a very large number, favors products quite a bit. Hydrochloric acid, HCl, is a little bit weaker. It's 1.3 times 10 to the 6th. And then you have something like nitric acid or oxy acid, which we consider 100% ionization. But really the K value is only 24. It's really not that large. But if you look at the comparison to our weak acids here, you can see it's much lower. Hydrofluoric acid, benzoic acid, acetic acid, all those values are on the order of 10 to the minus 4th, minus 5th. So the equilibrium actually favors reactants more, and you don't get nearly as much dissociation, which is why they typically show 5% or less ionization. Those weak acids do. We can also look at the strength of a base by looking at the equilibrium. So if we're looking at a base and its interaction with water. This is our base here, and it's going to pick up a proton from water, which is acting as an acid in this instance. And as a result, we'll create this conjugate base and conjugate acid pair, right? So the strength of the base is dictated by the interaction between the conjugate base and conjugate acid. If there is reactivity between OH minus and this conjugate acid, H base over here, then you'll see back reaction, and that weakens this, makes it a weaker base, right? Because it's going to react in the back direction, and the K value is going to be weaker. But if there's really no interaction between these two, we could write this as a single arrow and say it's a strong base. So if we look at the equilibrium constant we could write for this, our products are OH minus and this conjugate acid version of the base, which show up here in our numerator, and our reactant is the original base there, but H2O doesn't show up because it's a liquid. This is known as a Kb value, or a base dissociation constant. So whenever we're talking about acids or bases and their dissociations, we use the subscript A or B there to talk about a base. We use B. To talk about an acid, we use A. That's how we distinguish between the two. As we talked about earlier, that lowercase p just means negative log. So a lot of times when we're dealing with Ka values you saw for those weak acids, you'd get values on 10 to the minus fourth. To make it a more manageable number, we like to look at pKa, right? So if you have a really low pKa, we could also look at pKb, by the way. A really low pKa and a really low pKb, that tells you have a really strong base. So the strength of this interaction is determined by the K values here, right? So a larger Ka value means a smaller pKa. So if we have a strong acid, right, then we're going to have a really large Ka value, and that's going to give you a really small pKa because this is a negative log, right? That negative term means you're going to have the opposite effect. And the same thing for a base. If you have a really large equilibrium that favors products, that's going to give you a small pKb, which means you have a strong base, right? Okay, so many reference books only give values for Ka. That's just kind of by design. In the convention of chemistry, we always give acid dissociation constants. So where do we get base dissociation constants? Well, it turns out that we can actually figure that out. So if we think about the reaction we have below, this is our acid, HA, and in this reaction, water acts as a base, and our acid is going to form a conjugate base pair, and the base is going to form a conjugate acid pair. All right, so if we focused on the strength of the base, right, the reaction in the reverse direction tells us how strong of an acid that is. So we need to look at that conjugate base to see, well, what's the reactivity like for that conjugate base, right? How strong of a base is it? If it were to react with water, okay, and it's acting as a base, then it should be able to abstract a proton, and you would get the acid back, HA, and you'd be left with hydroxide, OH minus, right? So this would give us an idea of how strong that conjugate base were, and we could look at the equilibrium here, and we can write a Kb expression for that, right? So this is what our Kb expression would look like. We would have HA, OH minus in our products, and then A minus, which is the conjugate base we got from the acid dissociation, would show up here in the denominator, right? So if we add these two reactions together, we see that the acid HA is going to cancel out. All right. And the conjugate base A minus is going to cancel out. What does that leave us with? 2H2O gives us H3O plus and OH minus. That looks awful familiar. That is the autoionization of water. So what does this mean? Well, we know that if we're adding two reactions together, you have to multiply their K values together, right? So let's think about what happens when we multiply Ka by Kb. Ka here is A minus H3O plus over HA. Kb, HaOH minus over A minus. Right? When we multiply those together, A minus cancels out, HA cancels out, and we're left with H3O plus times OH minus, which we know is Kw. So what I've just proved to you, right, using mathematical reasoning, is that Ka multiplied by Kb will always give you Kw. So if you're only given Ka and you need to find Kb, well, you know that Kb equals Kw divided by Ka. And also vice versa, right? Ka equals Kw divided by Kb. So we can figure out acid dissociation or base dissociation constants using these relationships. All right, so just a quick comment on some trends and strengths of these acids. I don't know if you remember from the previous slide. We'll see if we can go back real quick. I had some, here we go, I had some Ka values up there. And if you look at hydrobromic acid up at the top here, it's got a Ka value of 1 times 10 to the 9th. And then if you look down here at hydrochloric acid right below it, it's got a value of 1.3 times 10 to the 6th. So obviously hydrobromic acid is a stronger acid. The question is, why is it stronger? So there are some trends in binary acids that we can look at. And we could say, okay, well, you know, the strength of the acid is dependent on the ability of hydrogen to ionize from the molecule, right? So if we have a really polarized bond, the more acidic it should be, right? So we could look at polarity, and we could reason that the stronger this dipole moment is, the weaker the hydrogen is, and the more readily it'll pop off to create H plus in solution, right? So what we see is that as you increase electronegativity, you get increasing acidity. And we know that as we move from left to right in the periodic table, if we're in the same period moving left to right, we're going to get more electronegative anions, this X value there in the binary acid. So we polarize the bond more, and that makes the hydrogen more labile, more ionizable. So H2O is a weaker acid than HF, right? Even though HF is a weak acid. HCl is a stronger acid than H2S. HBr is a stronger acid than H2SE. Okay. Now, as we go down, we also increase acidity. And so why is that, right? We just talked about how you polarize the bond more, it makes it more acidic. But think about what happens as we go down a group, right? Here we have fluorine, F, and here we have chlorine. So, change colors here. All right, we got fluorine here, and then we got chlorine, and then we got bromine. What happens as we go down that group? Well, this should have the highest electronegativity in fluorine, right? And then this should have a little lower electronegativity. So this would be the second in terms of the electronegativity. This would be even lower. This would be third on our electronegativity scale. And then this would be last here, right? This would be the least electronegative iodine. But we see that this is the most acidic, and this is the least acidic in terms of strength. All right, so what's going on? Well, when you go down a group, there's a size effect that's occurring. So if we look at this size effect down the column, we see that HF is actually the weakest acid and HI is the strongest acid. So if you think about these binary acids, all right, hydrogen doesn't change. It's all got the same size. So this is our hydrogen atom, right, and it has a certain size to it. Okay, there it is. It's not going to change no matter what the acid is, right? And so we'll look at H. Oh, that's a terrible H. Let's do this again. HF, HCl, HBr, and HI. Now, what does change in these binary acids is the size of the anion, right? So if we were to look at these anions in terms of their size, we'd see that, you know, fluorine looks something like this in terms of its size, right? So it's kind of pretty large. But if we go up to chlorine, we're going down a whole row in the periodic table. So that chlorine is going to be much larger in size, and as it gets larger in size, it weakens the bond between hydrogen and chlorine. So this has a much weaker bond, which makes hydrogen more labile. As you go down to bromine, this gets even bigger, right? The anion gets even larger. And then when we get to iodine, that's when we're at the largest here. Iodine's huge compared to those acids. So if we think about bond strength, right, we have the strongest bond in HF, and then we have the weakest bond in HI. So even though fluorine's more electronegative and the bond's more polar, it's also stronger because of the size here, right? So this is fluorine, chlorine, bromine, and iodine. When you get these really large, bulky anions, there's just no interaction keeping that hydrogen there, so it could leave easier, it can ionize much easier. And that's why it's a stronger acid. All right, so here's the bond energies, just to give you an idea of this effect. And you see there's a really high bond energy with HF. So the bond is a stronger bond than something like HCl and HBr. You can see how bond energy here, as you go down this group, your bond energy is decreasing, but your acid strength is increasing, right? So as you go with decreasing bond strength, that gives you increasing acidity. So it's an inverse relationship here. Okay, now for oxyacids, our electronegativity effects are a little bit different. So just to refresh you, an oxyacid is anything that has the hydrogen attached through an oxygen to the central atom. So if you think about nitric acid, HNO3, our nitrate has this type of a setup, and our nitric acid then would have a hydrogen attached through one of those oxygen groups. Okay, so that would be our nitric acid. Actually, we should have two double bonds there. All right, so this is what nitric acid would look like. And the hydrogen then, the acidic hydrogen here, is this hydrogen. And this hydrogen can come off into solution to create H+. So what we're going to focus on is what we call the Y, which is the central atom in that oxy acid, right? So we see that something like HClO is a much stronger acid than HIO, and this is an electronegativity effect. So as you go down a group, right, if we're thinking about going between the series of HClO, HBRO, and HIO, right, this series of oxyacids, where the central atom here is going to be chlorine, bromine, iodine. This has greater electronegativity, chlorine does, and this iodine has the lowest electronegativity. So because you have a higher electronegativity, you weaken the OH bond more. Remember, the hydrogen, it's not like what we saw earlier. The hydrogen here is attached through the oxygen to the chlorine atom. So the acidity is going to decrease because, this more electronegative chlorine pulls more electron density towards it. So that weakens the hydrogen-oxygen bond versus iodine, which is not electronegative. The hydrogen-oxygen bond is going to be really strong. And we don't see the size effect here that we saw with the binary acids because these atoms, even though iodine's really big, it's not attached directly to the hydrogen. It's attached to the oxygen atom here, which is then attached to the hydrogen. So there's not going to be a size effect at all. This is purely electronegativity effect. Okay, so the larger the oxidation number of the central atom, the stronger the oxyacid. And so what we see is something like carbonic acid is a much stronger acid than H3BO3, right? So boric acid. And so the acidity of oxyacids basically increases to the right across a period, and that has to do with the electronegativity effect as well. As you go left to right across the periodic table, you're increasing in electronegativity. So this does follow the trend of the binary acids. And then the more oxygens you have attached to your central atom in an oxyacid, the stronger the oxyacid is. So chloric acid, HClO3, is stronger than perchloric acid, HClO2. Right, 3 oxygens compared to 2. And this is also an electronegativity effect. So let's go ahead and look at that first series we talked about, chlorine, bromine, iodine. Here's the electronegativity of what we call the Y molecule, which is the central atom in the molecule. So that central atom has electronegativity of 3.0 for chlorine, and it goes down to 2.5 for iodine. And here are the Ka values, right? So obviously this is the much stronger acid because 10 to the minus 8th is a bigger number than 10 to the minus 11th. And if we look at oxygens that are attached, okay, we can say, well, let's go down the list of acids. This is perchloric acid, which has 4 oxygens attached to it. Okay, just one of those oxygens has the acidic hydrogen attached to it that can dissociate. Now the other oxygens kind of add to this electronegativity effect. So the more oxygens I have over there, the more they're going to pull electron density away from that hydrogen, making it easier to ionize. So this perchloric acid is actually considered a strong acid. It will 100% dissociate because of those oxygen atoms. You take one oxygen atom away to get to chloric acid, HClO3, and all of a sudden you lose that ability to ionize so readily, and you're not a strong acid anymore. Okay, so there we go. Let's go ahead and try some practice problems real quick. You have ammonia, NH3, which has a Kb value of 1.8 times 10 to the minus 5th, and hydroxylamine, H3NO, has a Kb value of 3.1 times 10 to the minus 8th. Which is the stronger base, ammonia or hydroxylamine? Take a moment to pause and answer that question. Let's go ahead and move on to the next question. Carbon dioxide in the atmosphere dissolves in raindrops to produce carbonic acid. So anytime CO2 can dissolve in water and create carbonic acid, and this causes the pH of clean unpolluted rainwater to range from about 5.2 to 5.6. So what are the ranges of concentration of H plus and OH minus for the raindrops? Go ahead and pause the lecture and calculate this on your own. Okay, one more thing we need to talk about is how to find the pH of a strong acid or strong base when you have a polyprotic acid. We talked earlier about how a strong acid like HCl will 100% ionize, so it's pretty straightforward to calculate this pH. If we know HCl is strong, well then it's going to completely dissociate to create H plus and Cl minus. So if I have 0.1 molar HCl solution, that means I'm going to create a 0.1 molar H plus and 0.1 molar Cl minus. pH then is just going to be the negative log of the concentration of H plus, which is equal to the negative log of 0.1. And so my pH would equal 1.00, right? What happens though if I have a polyprotic acid, something like carbonic acid, right? We just talked about how carbonic acid will actually, lost my mouse here, will actually give you acid rain, right? And the formula for carbonic acid was H2CO3. So obviously we put the acidic protons out front. There are 2 acidic protons there. So what does that mean for us? Well, there's one dissociation that occurs where a proton comes off to make H plus and HCO3 minus. And then that second molecule, HCO3 minus, can create another proton in solution and leave us behind with carbonate, CO3 2 minus. So when you have a polyprotic acid like this, the first step is the strongest step, the second step is weaker, and the third step is the weakest step. All right, so for a strong ionic base, we talked about how hydroxides can be calculated from the number of hydroxides multiplied by the concentration of base, and we can calculate pH from that. You could either calculate POH and then convert it to pH, or you could use concentration of OH minus and convert it to concentration of H plus and calculate pH. It's totally up to you, however you want to do it. All right, so the last calculation I want us to do is to calculate the concentration of an aqueous solution of magnesium hydroxide. It has a pH of 10.05. So what I want you to do is tell me, right, what is the concentration of magnesium hydroxide if our pH is 10.05. Go ahead and pause the lecture and try to calculate that in your note. All right, we'll go ahead and stop right there. That'll end Unit 2 of our acid and base section. And I'll follow up this lecture with worked out solutions to those problems from the notes.